Hi, it's Moser with a quick tutorial on binary ionic compounds. Naming them and writing them. After this video, you should be able to name any binary ionic compound when you're given the formula, as well as being able to write the formula for any binary ionic compound when you're given the name. You already need to know what anions and cations are. And, this is important, you need to be quick and fluent and familiar with the ions that are made by the main group elements. You ready? Let's go. So this video is going to serve as your introduction to chemical formulas, and I'll give a brief overview, but then we're going to concentrate on naming and formula writing for ionic compounds. For a molecular compound, the chemical formula shows the actual number of atoms in each molecule. Of course, we don't have that luxury with ionic compounds. Why not? There are no molecules in ionic compounds! You knew that. Because of that, the chemical formula for an ionic compound is what's called a formula unit. And all it does is show the ratio of ions, cations, to anions. All right, we're going to start off talking about simple monatomic ions. You know that mono means one, and monatomic ions are ions that are made from, well, a single atom. The main group elements, of course that's the S and the P block, tend to lose or gain electrons to achieve a noble gas configuration. You already know that. And these groups form monatomic ions. When we look at the S block, both groups 1 and 2 lose electrons to form cations, which you knew. And group 13, the first group in the P block, also tends to lose electrons to form a cation. Now, groups 15, 16, and 17 will form anions. In other words, they'll gain electrons. The D block is kind of its own weird thing, and we'll cover that later, but it's complicated. All right, so naming compounds. Well, in order to know how to name a binary ionic compound that's made up of monatomic ions, we have to know how to name the ions themselves. And we're going to focus on the simple monatomic anions and cations. The D block, again, we'll get to in a little bit. Don't worry about it yet. Cations, this couldn't be easier. Cations are just named for the element with the word ion slapped on the back. So, we find that the Na1 plus ion is called a sodium ion. Well, that was easy. The calcium 2 plus ion is called the calcium ion. Wow, really? That easy? Yeah, seriously, that easy. As you can imagine, magnesium 2 plus is called the magnesium ion, and potassium 1 plus is called the potassium ion. Aluminum 3 plus is called, I know you'll never guess, the aluminum ion. Okay, great, you've got that. Now let's talk about anions, because these get handled just a little bit differently. When we talk about monatomic anions, the ending of the element name is dropped, and it's replaced with IDE. So, chlorine gains an electron and becomes the chloride ion. Sulfur gains 2 electrons and becomes the sulfide ion. Oxygen, our old friend, gains 2 electrons and becomes the oxide ion. This seems really simple, but I'm going to warn you. This IDE ending is super important, and later we're going to have some other endings. So I want you to make a special note somewhere to yourself that IDE equals monatomic anion. Trust me, you'll be happy about that later. Okay, so to name a binary ionic compound, when you're handed a binary ionic compound, bi like bicycle, that's a compound made up of just 2 pieces, well, you name the cation and you name the anion, and that's the name of the compound. So NaCl, an ionic compound made up of sodium ions and chloride ions, is sodium chloride. Al2O3, an ionic compound made up of aluminum ions and oxide ions, is aluminum oxide. And calcium bromide is made up of calcium ions and bromide ions. It does not matter what the subscripts are. When we're talking about ionic compounds, we don't care about those subscripts. We only need them to know how many atoms are in the formula unit. Okay, this is pretty easy, so I think you're okay, but now let's get to the slightly more interesting part. That would be writing a formula when you're given a name. You will need to have your periodic table out, or maybe even the reference sheet that was linked in the chapter plan. All right, so we've already mentioned that binary ionic compounds are just compounds made up of two different ions. Seems easy enough, and we're starting off with binary ionic compounds that are made up of simple monatomic ions. Now, in a binary ionic compound, in order for it to be neutral, the total magnitude of the positive and negative charges has to be equal. So, when magnesium 2+ forms a binary ionic compound with bromine, bromide ion, bromine 1-, we have 1 magnesium and 2 bromide ions. That balances the charges. Therefore, we get MgBr2. The formula subscripts show you the ratio of cations to anions, and it's really simple algebra. The subscript on the first ion, which is always the cation, times the charge on the cation, plus the subscript on the anion times the charge on the anion, have to equal 0. They have to cancel one another out. So if we look at the example of Al3+ and O2-, the aluminum ion and the oxide ion, we know that our charge on aluminum is 3+, and our charge on oxide is 2-. Well, when we look at this, it seems like we should be able to figure out what would go in there to balance those. And in fact, if we multiply the 3 plus 3 by 2 and multiply the -2 by 3, we get 0. So our formula, because remember those are our subscripts, is Al2O3. Let's try another one. We're told that we have calcium chloride. Now, of course, you've got your periodic table, and you're completely fluent, and you know that calcium, being group 2, forms a, what is it? 2+ ion, and chloride, coming from group 17, has to be a 1- ion. So we're going to use the sort of set formula that we've got, subscript times the charge on the cation, plus the subscript times the charge on the anion, has to equal 0. Well, we put this down with some blanks, and pretty quickly we can figure out that that's got to be a 1 and a 2. Well, that gives us calcium with a 1 subscript, chloride with a 2 subscript, and you can see where those came from. Now, the fact is, we never put a 1 subscript anywhere. We just leave that with no subscript because the fact that we've written calcium tells us there has to be at least 1 calcium ion. Let's try one more together. We've got potassium oxide, and you've got your periodic table, so you know that potassium, which is in group 1, is going to form a 1+ ion, and oxide, our old friend, is 2-. So we write out our sort of formulaic subscript times charge plus subscript times charge equals 0. And we can pretty easily see that that should be a 2 and a 1. Well, what does that give us formula-wise? It gives us K2O. Where did those subscripts come from? Well, the 2 came from there, and the 1, which we don't write, came from there. All right, let's talk about one thing. You may have learned a different method in physical science. You may have learned the crisscross. Write down your ions, take the charge, write it as a subscript, voila, you're done. Same result. It's true, it is. And if you're used to using the crisscross, I don't have a problem with you using it. That's fine. But I want you to understand where those ratios come from, and that they are, in fact, a ratio. The other place that the crisscross sometimes gives people problems is in a compound like magnesium oxide. So go ahead, use your periodic table, write down your ions. Well, in magnesium oxide, of course, when we look at this, we can immediately see that those are going to be 1s, and our formula will just be MgO. But what if we were using the crisscross to find the formula for magnesium oxide? I'll show you the thing that people sometimes do. They crisscross those charges and get Mg2O2, which, while it is the correct ratio, is not a correct formula unit, because the subscripts in a formula unit have to be simplified. So again, if you're comfortable with the crisscross and you want to use it, that's fine. But please make sure that you understand where these ratios come from. Okay, you've got practice to do, so go do it.